You build a simple calculator application. You type a 12 in the dividend field, a 0 in the divisor, and you hit enter. Instantly, the application shatters. The window freezes, the buttons lock up, and the entire runtime environment abruptly terminates. Behind the scenes, the terminal spits out the autopsy report. The top of the stack trace shows the cause of death: java.lang.arithmetic exception, divide by 0. Java prevents this through 3 architectural layers, distributing responsibility across the system rather than relying on math logic alone. The first layer is the structural inheritance tree that physically constructed the text fields and buttons on the screen. The second is the event-driven system that processed the physical click. And the third is the bifurcated error boundary that should have caught the resulting anomaly. Writing a robust object-oriented application means assuming the user will eventually input something destructive and building a structure specifically designed to absorb that chaos without bringing down the system. To see how this works, we have to rebuild the application from the ground up, starting with the static layout. Every text box and button you see here is an individual object. In Java, these objects are organized through an is-a structural hierarchy known as inheritance. A text field doesn't exist in isolation. A JText field is a J component, tracing its lineage up a rigid family tree. This design utilizes software reuse. A new child class or subclass automatically absorbs the variables and methods of its parent superclass. Developers don't have to rewrite the core logic for rendering shapes or capturing text, but there are strict rules for bringing these objects into existence. A subclass object cannot be fully instantiated until its foundational base state is established first. When the calculator asks for a new button, the memory allocation process must trigger the button's constructor, which then automatically executes the constructor of the class above it, all the way up the chain. Programmers control this initialization explicitly. By placing the super method on the very first line of the subclass constructor, they guarantee the parent state is firmly initialized before the child class adds its own specific features. This hierarchical chain connects modern, lightweight swing components, like our calculator buttons, deep down to the older abstract window toolkit foundations that interact with the local operating system. It also cleanly separates the individual component classes from the container classes, like a JFrame, which act as the passive structure holding everything in place. Because of this structure, developers can endlessly extend a base class to create highly customized input fields without ever modifying the underlying proven framework. The button you click on the screen appears simple, but it only exists at runtime because of a deep historical sequence of inherited methods passing data down from generation to generation. Once the static architecture is drawn, the application enters a completely different phase. It has to wait for a user to do something. This is event-driven execution. Instead of reading a script linearly from top to bottom, the program enters a continuous holding pattern, waiting entirely on external stimuli. Within this holding pattern, the roles of the GUI elements split. The containers remain passive, holding the layout, but the individual components, like a text field or an equals button, stand ready to actively generate signals based on whatever the user inputs. When a user strikes a key or clicks the mouse, that physical force is instantly translated by the component into a digital signal. In Java, this signal is packaged as an event. It is a data object that encapsulates the exact specifics of what just happened: which button was pressed, where the mouse was located, and what text was entered. But an event is useless unless something is listening for it. That is the sole purpose of a listener object. It monitors the application state, waiting exclusively for a specific component to fire a specific event pulse. The system won't do this automatically. The programmer has to explicitly write code that registers the listener object to the component, binding them together. This is a strict architectural decoupling. The visual presentation knows nothing about the math logic, and the math logic only runs when the listener hands it an event packet. It is a controlled way to manage highly unpredictable, asynchronous user behavior. Now we return to the exact moment our calculator crashed in Act 1. The listener received the click event from the equals button and handed the data to the math logic, but the user entered a 0 for the divisor. The execution hits the division operation, and the computer finds the request mathematically impossible. A novice programmer might try to prevent the resulting crash procedurally. They will wrap the division logic in an if statement, explicitly checking if the divisor is not equal to 0 before proceeding. But this procedural approach is fragile. If the user accidentally types the string 2e instead of an integer, the if statement doesn't catch it and the program crashes anyway. Trying to anticipate every single incorrect input forces you to mix exhaustive state-checking gates directly into your core application logic. The code becomes difficult to read, nearly impossible to modify, and ultimately fails to protect the runtime. The structural alternative is Java's exception handling mechanism. Instead of policing the input before execution, you build a designated failure route alongside the main execution path. This slide formally defines an exception as an occurrence of an undesirable situation that can be detected during program execution. Notice that division by 0 is cited as a primary example. The mechanism starts with a try block. You place your risky execution logic inside it. If an anomaly occurs, the remaining statements in that block are immediately ignored. Normal top-down flow comes to a hard stop. The program creates an exception object representing the error, and the Java virtual machine begins hunting downward for an appropriate handler. That handler is the catch block. If its parameter type matches the thrown error, like an arithmetic exception, the catch block activates and safely intercepts the error object before it can kill the application. Looking at this lecture slide, we see the overarching architectural goal. Exception handling enables programmers to completely remove error-handling code from the main line of the program's execution. Application robustness isn't achieved by writing perfect procedural if statements to dodge fatal errors. It is achieved by recognizing that failures will happen and building a structural pipeline to safely route and manage them as expected data objects. Let's run the exact same input through the calculator again, tracing the execution through the completed 3-layer architecture. Once again, the user types a 0 into the divisor field on the screen and forcefully hits the Enter key. First, the UI component capturing the text is stable. It established its memory footprint at launch because its constructor invoked the super method to inherit its base state. Second, the presentation layer knows better than to attempt the math itself. The component cleanly decouples the interaction, firing an asynchronous event pulse to the registered listener object. Finally, execution enters the listener's try block. It attempts the division, and the math inevitably fails. But this time, the bifurcated control flow catches the anomaly. The JVM immediately suspends the try block and hands the arithmetic exception object straight into the matching catch block. The catch block executes its recovery logic. It reaches back out to the graphical interface and gently informs the user on screen, cannot divide by 0. The application remains running. A single successful click requires deep engineering. Superclass constructors initialize the environment. Listener events decouple the interactions, and try-catch boundaries isolate the failures. These mechanisms exist to absorb chaos, ensuring the application outlives the inevitable mistakes of its users.